Hello everyone, I'm Reza Taghavifard and today I present our paper Design Space Exploration of Freeform Shells through Conditional Variational Autoencoder. Supervised by Dr. Morteza Rahbar, this project was originally my master's thesis carried out about 3 years ago. In architectural design, the challenge is to navigate a very large design space. On the left side, the diagram shows the typical fabrication-aware design workflow. We start with input parameters, run computational models, evaluate performance, and then adjust based on fabrication constraints. This loop is effective, but is slow and requires constant iteration. On the right, the 3D surface represents the design space itself. Two axes for input parameters and the vertical axis for performance. Each point is a possible design solution, but the space is full of peaks and valleys, which makes finding meaningful solutions very difficult. Traditional optimization methods can search these landscapes, but they often turn exploration into a black box. The process becomes intuitively weak because designers are not directly involved in shaping or steering their solutions. Our goal in this project was to create a framework that keeps the designer in the loop, making exploration interactive, intuitive, and performance informed. To train our model, we first generated a large dataset of shells using custom Grasshopper codes. We created about 30,000 geometries covering three curvature types: parabolic surfaces, which were cylindrical single curvature; elliptic surfaces, which were domes with positive curvature; hyperbolic surfaces, saddle shapes with negative curvature. This diversity captured a wide spectrum of structural behaviors, giving our model a rich training dataset. Each geometry was discretized into a uniform 21 by 21 grid and analyzed using the Karamba plugin in Grasshopper. We measured maximum displacement under gravity as our structural performance metric. To prepare for training, shells were also converted into grayscale images at 84 by 84 resolution and augmented to expand the dataset to 90,000 samples. This ensured both geometric diversity and structural feedback were embedded in the data. We implemented a conditional variational autoencoder with this architecture that you are seeing now. The encoder compresses each shell into a 16-dimensional latent space, and the decoder reconstructs shells conditioned on the maximum displacement value. By embedding a structural performance directly into the latent code, the model doesn't just learn geometry, it learns how performance and shape are connected. Because our dataset included geometrically diverse shell types, parabolic, elliptic, and hyperbolic, the model could recognize what changes are needed in a given geometry to improve its structural behavior. In other words, the CVAE doesn't only reproduce forms, it also learns the logic of how curvature influences performance, enabling it to generate structurally informed variations. Even 16 latent dimensions are difficult to interpret, so we applied TSNE to reduce them into a 2D space for intuitive navigation. The challenge with TSNE is that it's not reversible, so we trained a deep neural network to map from the 2D embedding back into the latent space. This means that designers can not only visualize the design space but also click on the map and regenerate the corresponding shell geometry with structural conditioning included. The results were very promising. The database of 30,000 shells revealed clear structural patterns. Hyperbolic shells consistently had lower displacements, while domes and cylinders behaved differently. The CVAE plus TSNE plus MLP framework that we trained for making TSNE reversible produced an interactive 2D design map where designers can explore geometries based on both shape and performance. Generated shells often blended curvature types but still responded to the conditioning variable, showing that the model truly learned the geometry performance relationship. So we can give a shell to our model and making it slightly better by exploring the space provided by TSNE algorithm. That was the main achievement of our model. To summarize, this work demonstrates a performance-informed generative framework for exploring freeform shells. It allows designers to navigate a vast design space intuitively while still accounting for structural feedback. Thank you everyone for your attention.